So now, after that, so this is when we consider an equimolar mixture of these, right? So we talked about this. So if you add an acid, go back to the two components. So you have to have two components in your buffer because you have to be able to cancel any strong bases added or any strong acids added. So there's always going to be two components, and each component plays a role. So for example, when we add a strong acid is added to the buffer, we have to protect the pH from dropping. Well, how do we cancel that out? Mop that up. What are we going to use to mop that up or wipe that up or whatever you want to call it? Absorb it. What's going to absorb it is that's where the conjugate base comes over, grabs the H. You're going to put together a little bit of the weak acid, but what it does is it prevents the pH from changing. The pH will barely change like you saw in that little cartoon or that picture I showed earlier. So what's going to happen is you start with equal amounts. You'll create a little bit more weak acid and a little less conjugate base. Why? It's like if you use up paper towel, the roll is going to be a little smaller. Think about it that way, and we produce the other version of it. Now, if you look right here, so it's just like this, almost H plus, or you could write H3O plus. H3O plus A minus, boom, is going to get you HA plus water, is essentially what you're going to get. But it mops it up. It soaks it up. We're soaking up that H3O plus. We're preventing from the pH from dropping because remember, a buffer resists changes in pH. When a strong base is added to a buffer, what do we know cancels out a base? We need, in order to cancel out or absorb a base, we need an acid. So that's where the weak acid kicks in. Here's my HA, my weak acid. OH minus is going to kick in. What is that going to do? It's going to put an H over there, which is going to turn into water, and then it's going to leave a little bit conjugate base. So if we go and take a look here, there we go, boom, we have OH minus being added. Weak acid donates its H. We get water, and we get a little bit more. We're using up some of our weak acid, so we have a little bit greater amount of our conjugate base produced as a result of preventing the pH from changing. Now, the other aspect of this is, whoops, I didn't add the slide, whoopsie-daisy. The other aspect of this is you have to be able to calculate out the pH. You want to know the good news? You already know how to do it. I taught you the Hasselbalch equation for when we're before equivalence, when it's a buffer solution. So we're using the exact same thing you've been using and you used in your homework. You're going to get pKa, which is just the negative log of the Ka. You're going to pop in the acid molarity there. You're going to pop in the conjugate base molarity there. Now, how do you spot the problem? It's going to be pretty easy. When you roll up, I cross out any cross-out ions. And there's two molarities. That's how you can tell. Plus, this says what's the pH of the buffer solution. The AP exam, they don't always come out and say that, so just so you know. Well, sodium formate is formic acid. It would have the Ka listed on the AP exam because you don't get a table. So it would say 1.8 times 10 negative fourth is the Ka for HCOOH, formic acid. So the first thing we're going to do is we're going to take the negative log of that. So I'm going to go 1.8 E for negative, log, sign change, I get 3.74. That represents my pKa. So all I do to get pKa is I take the negative log of my Ka. That's what you see me doing right there. Boop, I got that right there. Then I'm going to stack the molarity of the conjugate base on the top, the molarity of the acid on the bottom, and they're going to be given to me in the problem. Well, take a look. There's my acid, a weak acid. Nothing's going to cancel, right? Plus, you should be able to spot a weak acid anyway. So I go log. I'm going to put 4.05 on the bottom, 0.405 on the bottom. This is my conjugate base because it's a negative ion. After I cross out the cross-out ions, is what you're supposed to do in any pH problem that we get, 3.26. So then I'm going to just pop that in my calculator. So I go 0.326 divided by 0.405. Boom. I'm going to log that. That's going to give me negative 0.094, and then I'm going to add that to 3.74, which means my final answer is 3.65 would be my pH. Now, notice it's slightly lower than my pKa value. Why? Well, if you look over here, the solution contains more of my acid, my weak acid, than my conjugate base. So that's why it's going to be slightly below pKa. You can kind of tell from the ratio, because this is a ratio of conjugate base to acid, where it should be the pKa value, if it's going to be above or below. If they're even, it's equal to the pKa value. Remember, we learned maximum buffering when we're talking about titrations, halfway to equivalence. So if this is equal to 1, the log of 1 would be 0. That's where pH is equal.